All right. Let's see. So I have a warm-up here. Oh, okay. Yeah, my warm-up is we're just going to look at something together real quick. That's 6. Okay. So what we're going to just do real quick is we're going to look at, remember I told you guys, try to review ellipses and hyperbolas. I'm going to do a little bit of review with you guys as well. So let's consider the graph of the ellipse given by x to the 4th over x squared, sorry, plus 4, and then y squared over 9. Then we're going to look at it with 1, and then we're going to add a k to it, a random scalar k. That's what's going to get funky. So let's look at what's going to happen with that on Desmos. Take a look. Okay, let me see. Make sure that this is connected. Oh no, what's going on? Hold on. It's on, right? Oh, thank God. Okay. Okay, so let's see. Let's go to Desmos. Let's play around with this. You guys can ask questions as we do this. Okay, so here is my ellipse, okay? Right now, k is 0. So pretend it's just x squared over 4 plus y squared over 9 equals 1, because k is 0 right now. So remember that for ellipses, you have some constant, you have some number under x. The general form that you guys learned in pre-calc, or whatever class that was you learned this form that looked like this, okay? And what the value under x squared was telling you, it was telling you the square root of that number tells you how far it stretches in the x direction. And then the square root of the number under y tells you how far it stretches in the y direction. So it's kind of like a circle that's being stretched so that it doesn't have the same radius all over. There was all kinds of other stuff you guys learned, something called a foci, and there was all other stuff that you probably don't remember. It's all good. We're not going to do any of the other fancy stuff. All we care about is the general shape of the ellipse. I need you guys to just remember, if that was a 4, then in x, it goes from -2 to 2. If it was a 25, then x goes from -5 to 5, and so on, right? If this was 36, then the y values go from 6 to -6. That's the basic structure that I want you guys to remember for ellipses, okay? Yes?
Well, I think, let's say there's the centimeter axis, like,
You mean like kind of like the diameter of this thing? There was different names. The smaller one was called the minor axis, and the longer one was called the major axis. Sure. Yeah, like half of that. And the ellipses that we're going to look at in this class are centered at the origin. Sometimes they're not. We'll deal with them in those very special occasions. But like if I wanted to move the x values, if I wanted to move it so that it goes to x equals 7. See, now the ellipse got moved so that it's at 0, 7. Right here. It's centered there. Kind of like a circle. Remember that? The circle changes the center. It's very similar. Again, we're going to just keep it basic, and we're just going to be dealing with ellipses that look like this, that are centered. Okay? But if I have a 1 minus k here, this is where it gets funky. To get this general form, I'm going to want, like if k equals, let's say k equals -2, let's say -3, then now I have this right here, right? So this general form, though, I want it to be a 1. So then you would just divide everything by 4. Okay? But what I want you guys to see is for different k values, I just want you guys, let's just play around and look at what happens to the graph. Let me go back to the original 4 and the original 9. So notice that as k, if k is where was it? 0, right? Here's k being 0. If it starts increasing, then it's going to get smaller. Notice that it gets smaller, it gets smaller. It's getting close to 1, and then boop, then it's a point. Okay, let's see why it's a point. We can't even see it. Okay, what happens if k is equal to 1 here? It's going to equal 0. And what I want you guys to observe that on the left-hand side, I have x being squared, which is positive, over a positive. So this whole fraction is a positive. Sorry, not a positive. It is, that whole thing is not negative. X squared over 4 is not negative. Can't be negative because it's being squared. And this can't be negative either. So what are the only two things for x and y so that when you add all this up, it gives you 0. 0, 0, the origin. So when k is 1, you have an ellipse, but it's really just a point in the origin. Okay? And then when k is bigger than 1, let's say k is like 1.5, what do you get when you do 1 minus k? Negative. Can two non-negative things add to something negative? No. So in that case, there is nothing. There is literally no graph. It does not exist. Okay? But once k is 1 or something less than 1, then I want you guys to notice, oh, damn, it's going hella fast. Hold on, chill. Hold on, let me, let's go here. So it's like the ellipse is getting bigger and bigger and bigger and bigger. Okay? Why is that happening? Remember, I want this to be equal to a 1, right? So we're going to divide all this by this value. Okay? So let's see. I divide everything by this value. I'm going to divide this by 1 minus k, and I'm going to divide this by 1. But what happens when I divide this fraction by this value? You multiply the reciprocal. So it really becomes x squared over 4 times 1 over 1 minus k. So then the 4 and the 1 minus k just end up multiplying. Okay? So then it ends up looking like this. Same thing with this one. Equals 1. Okay? This tells me that as k gets more negative, what happens to this number down here? Think about it. Let's say k is negative 10. This is 90. No, negative 10 is 11, right? It'll be 11, 10 to 9, so that's 99. What does that mean? I take the square root of 99, and that's how far it stretches in the y direction. But if I make this 100, negative 100, now I got negative 100, 9 times 99. It's a big number. But I just want you guys to notice, as k gets more negative, what happens to the denominator? It's getting bigger, which is why the ellipse is getting bigger. Because the same thing is true about this. As k gets more negative, this number starts to get more big, it gets bigger, which is why the ellipse is getting bigger. You guys kind of see that? Yeah, a little bit. Okay. That's the kind of stuff we're going to kind of play around with today, okay? So I want you guys to just notice that. And you're going to see it. It'll make more sense in a little bit. But notice that as k gets closer to 1, the ellipse gets smaller. But as k gets more negative and away from 1, it's getting hella big, the ellipse. Okay? That's the kind of thinking we're going to do today to help us eventually sketch something in 3D. So I just kind of wanted to warm you guys up. Give you a little bit of ellipses. Okay, let me start sharing my screen. All right, here we go. Let's have some fun. All right. Okay, guys, so we're gonna finish off section 12.6 on something called the quadric surfaces. So what is a quadric surface? Let's start with that. What is that? So we're gonna say a quadric surface is the surface of a quadratic equation in x, y, z. So if you have an equation that has x, y's, or z's, and it turns out to be a quadratic, then its graph is what's called a quadric surface. Someone just shout, give me an example of a quadratic equation in x, y, z. Huh?
X squared plus y squared plus z squared equals 4.
X squared plus y squared plus z squared equals 4. Okay. Give me another one. Someone from this side of it. Give me a quadratic equation of x, y, and z. Remember, quadratic just means that the highest power is 2, but it doesn't mean that all the exponents have to be to the second power. Right? So, for example, I could also write something like this. Okay? Yeah.
What do you call the surface of a fourth equation in x, y, z?
What do you call the surface of the what?
A quartic equation like x to degree 4 in x, y, z?
Guess maybe a quartic surface. That that one's real. Those are really probably a little bit more complicated. There's a name that generalizes surface for polynomials in 3D. Let me remember what that is. Okay. What's the degree of this term? 2, right? What's the degree of this term? 1. So remember, quadratic just means you're going to have a polynomial where the degree of the terms is the highest degree of each term is 2. Okay, so I could also have something like this. Okay, because this is like each variable is of degree 1, when you multiply them, now they're going to be of degree 2. Okay, so these are examples of quadratic equations in x, y, z. And we're going to look at these surfaces of these guys. We're going to call them quadric surfaces. Sorry, my iPad always shuts me off. So how the heck are we going to graph all this stuff? So to help us graph quadric surfaces, we will intersect them with the coordinate planes. Remember what I mean by coordinate planes are like the xy, the xz, and the yz. We'll intersect them with the coordinate planes and analyze the intersection curves called the traces of the surface. I'm running out of space. Called the traces of the quadric surface. Prepare that. Here, let's see. Hold on, I got something prepared for you guys. There we go. Okay. So again, it's very visual. So let me go back here. Let me show you guys. Okay. So let me show you what I mean by all this. Okay. So you guys see this guy right here, this polynomial right here? Z equals 2x squared plus y squared. That's a quadratic equation. Okay. The graph of it, right now I'm showing it to you, turns out to be this kind of like three-dimensional parabola called a paraboloid. Okay. And this is what we're gonna do though. Do you guys see let me move this to 0. Do you guys see how right now this plane, this blue plane, is the x? This is the x-axis, the red one is the x-axis, and then the blue one is the z-axis. So this is mimicking the xz plane. Is that okay? Do you guys see how it's intersecting it? And it's the shape that it makes. What's the shape that it makes where it intersects it? That parabola is this parabola that I have graphed here. Let's see if it's this parabola that I have graphed here. Okay. What we're gonna do, and this is the part that's gonna be tricky, okay? In our heads, is we're gonna move in our heads and algebraically. We're gonna move the xz plane. When on the xz plane, which coordinate is 0? Y is 0, right? So y equaling 0 gives you the xz plane. That's what this is doing right here for me. It's letting y equals 0. Okay, is that cool? What we're going to do is we're going to shift that plane. We're going to increase the value of y, so then the plane will go forward in the y direction. But as it does that, I want you guys to keep in mind the intersections that that plane is doing with that parabola. Okay, so notice if I move it a little bit up, do you guys see this parabola right here? Is the vertex still at the origin? No, it's like a shifted up parabola, right? That's this parabola that's shifted over here. Okay. So as y is increasing, those parabolic intersection curves are going up. But here's the part that's gonna be hard. We're gonna do this 2D on a piece of paper. We're gonna look at the parabola going up, but what I need you guys to understand is that parabola isn't just on the xz plane, it's also kind of like moving up this way. That's going to be the hard part. Okay? It's moving up this way, the way this parabola is located at a different location of the y coordinate compared to the parabola over here. Now it's a little bit more behind that other parabola. So it's like, again, remember I told you guys the Disney Channel thing? Kind of like if you're in a VR and I'm painting with a rod, I would draw the first parabola here, hitting the ground, but then I would walk a little bit forward and I would put the parabola in front of it, but now a little higher. And then I would walk a little bit more forward, and then I would draw the parabola a little bit higher, but also more in front. Okay, those are called the traces. These guys right here, these intersection curves. Okay, we're gonna do that. These are called the traces for y equals k, where you're varying y. Okay, let me go back to 0. Okay, now we're gonna look at the traces for z equals k. So now, when z equals 0, what plane is that? The xy plane. As I increase z, what's going to happen to the xy plane? It's going to go up. And I want you guys to notice, when it goes up, see right now it's intersecting it right at the bottom of the paraboloid. Just a point, right? But as it goes up, those intersections are those elliptical curves right here where it's intersecting. And as I increase z, what's happening to the size of the ellipse? It's getting bigger. But where are they positioned in 3D space? So it's getting bigger, and they're like kind of like yeah, kind of like a bunch of rings that are placed on top of each other, but the rings are getting bigger and bigger as they're getting placed on top of each other. Okay. Yes, exactly. Yeah. Now, what happens when z is less than 0? What do you think would happen? It's not intersecting the paraboloid. So therefore, there should be no traces. We're going to see that algebraically when that happens. Okay. This is going to be a variable. Remember, we couldn't let k, when k was bigger than 1, there was no graph. And that means in 3D, there's a plane that is no longer going to intersect the curve. And so that's why that was happening, because in 3D, that's what's happening. Okay. You'll only have a graph when your planes of your traces of your variables, intersect the surface. Yeah. Here, let me show the class. In case you're wondering what you're talking about, it's that little stacking. Little stack right there. Okay, so those are what's called the traces for z equaling k. So let me go back to 0. So then there are the traces for x equaling k. Here, now when x is 0, what plane is that? The YZ plane. So now I'm going to let x increase. And again, notice the traces are just parabolas that are going to intersect it. Okay, and they're going up. Notice the trace, actually, yeah, this is a good point. Notice the trace when k equals +1, where's the vertex of the parabola? 0, 2. So if the plane is where x equals 1, what do you think the trace will look like if I make it so that now the trace is at x equals -1? Symmetry says that hopefully it's the same, right? Meaning the parabola should be the same trace, is just positioned in 3D space in 2 different locations. Let's see. So let me shift it to -1. Boom. We guessed it right. Okay. Let's see. Make sure I didn't miss anything that I want to mention. Okay. Let me see what I have here. So, we give you this handout. This is going to be pretty challenging to do. So what we're going to do, though, is these are the 6 main quadric surfaces that we're going to focus on in this class. There's a whole bunch of other ones, but these are the 6 main ones. And not only that, these 3 are really the main ones we're going to see a lot, especially when you guys get to integrals. Okay, you're going to have to graph these a lot. Okay, these top 3. So we're going to start with that training today, and they each have their fancy little name. Okay. Next to them shows you the general form of what the quadratic equation will look like so that it produces a surface of this type of shape. So let me pass these out. You're going to use them today. 1, 2, 3, 4, 5, 6. Oh, that's a good point. So the question was, are the traces the same for YZ and XZ? So let's let X equal, right now X equals -1, right? Let's see what happens when I remove, let's see what happens if I do it for this one. So they're not necessarily the same, depending on the value. And that has to do with the fact that this is not a perfect circle. It's an ellipse. So these traces will have a wider parabola, but then these traces will have a skinnier parabola. Yeah. And that will show up in the algebra. Yeah. Good question. Actually, I'll leave this here. Well, I pass these out. Okay, 1, 2, 3, 4. 1, 2, 3, Alright. I got it. Sorry, I think I didn't see that. You'll encounter them enough that you're gonna see patterns on them. Yeah, listen. Today's your first day, so yeah, they look a little overwhelmed. I'll take that. Okay. So just hold on to these. You're gonna use them in a little bit. Thank you. So what I want to do is the one that we just looked on GeoGebra. Let's see how we would do that manually without a graphing device. Okay. So let's work that one out. Let's see, how would I do what I just did by hand? So let's take a look at that. It's recording. Okay. So it'll say something like this: use traces to help you sketch the surface of, it was z equaling 2x squared plus y squared. Okay. So let's start with x equaling k. Let's start with x equaling k. So traces for x equaling k. When x equals 0, what coordinate plane is that? Which, so it's going to be, we're shifting the YZ plane. Okay. Okay. So let's see. What does that mean? That means we were letting x vary. So we're letting it equal a constant k. So what you're going to want to do is plug in that k in for x into the equation. So then now this becomes this, z equaling 2k squared plus y squared. Notice, what are the only two variables in this equation? Y and z, right? If I write it like this, y squared plus 2k squared. This is really just the dependent variable, like the y, equaling the independent variable plus some stuff. Okay, don't write this next part. What did the graph of this look like? Your brain now knows that, right? It's like, okay, it's a parabola, but what about it? What does a 5 do? Shifts it at 5. In which direction is the parabola facing? Which axis? Like if I was to graph it like this, is the parabola like this or the parabola like that? It's the first one, right? So notice it points in the direction of the isolated variable that is not squared. Okay. So if I use that same argument here, and this is really just the YZ that's being shifted. So I'm going to let Y here and I'm going to put Z here. This is a parabola. When K is 0, where's the parabola at? That's the origin, right? That's the origin. What happens as K becomes more positive? It's shifting, it's adding more, it's adding a positive, right? So that's going to force it to shift up. And actually, let me graph it over here because I want to label it a little bit more. Sorry, you don't have to erase it. It's too low for me. Okay. It's like this, and then it'll go up like that. So here, for example, is when k was 0. Here is when k, let's pretend this is when k is 1. But what if k is -1? It's the same. Remember, but remember, we saw that it could be the same. It's just in 3D, it's actually going to be in two different positions. So what the textbook is going to actually write, they're going to write plus or minus 1. Okay. What happens if I keep increasing k? It's going to keep going up. So these are the traces for x equaling k. It's parabolas that are moving up.
Does it continue to get extended?
Since this only affects shifting, it doesn't affect any stretching or compression.
It just move it up and up.
It literally will just move it up. Yep.
What situation was it again where the trace would just like disappear because it
It'll be does this example show one? Yeah, we'll get there.
Okay.
Hold on. You're gonna see an example. It's basically when k gives you something that will be undefined.
Okay.
In this case, that's not happening. What does that mean? That means that when I let x equal any constant k, it's always intersecting the surface. It's always going to intersect. Because no matter which k I plug in, this is defined. Okay, let's look at the traces for y equals k. Which plane are we moving in that case? The xz plane, right? When y is 0, this is just the xz plane. It's shifted. Okay. So now I'm going to restart again. And with my polynomial, my quadratic equation, I'm going to substitute y to be a constant. What do you guys notice about these these graphs here? What kind of traces are we going to have? You're also going to have parabolas, but now we're going to have it in the x z plane. Which direction are the parabolas opening? Z. And if here's a little knowledge of transformation. What happens when you put a 2 in front of the x squared versus when there was no 2? Yeah, remember, like if I have something like that with transformations, what does that 2 do to my function? It stretches it in the vertical direction. Okay, so these parabolas, when they were not stretched, now they are stretched. So what do you think they're going to be? Are they going to be fatter or are they going to be skinnier? It's going to be skinnier, right? Which is what we saw on GeoGebra. Some were fatter, some were skinnier. So here, let me move this down a little bit more. So here, the parabolas are going to be skinnier because they're being stretched compared to these ones. That's when k equals 0. What happens if I make k more positive or more negative? It moves the parabolas up, so they're going to be shifting up. But the shape of them will still stay the same. Okay, so here k could possibly be plus or minus 1. Okay, which one's left? X. Yeah. So let's do traces for z equaling k. Now we're shifting. Yeah, that's right. The xy plane. Okay. Here's where it gets a little bit more complicated. All right, we're going to substitute k into the equation for z. So now we get k is equal to 2x squared plus y squared. Uh-oh. Kind of wants to be a circle, but yes, but it won't, right? So what do you think the graphs for these are going to be? ellipses. But I want them to be in that general form. I erased it, sorry, that general, I want it to kind of look like this, right? You want the x squared, or you want the variable squared and the other variable squared, but you don't want anything in front of it. So you're gonna have to do a little bit of a little algebra trick. Okay. This is gonna be the same thing as if I do x squared times 2, which is the same thing as if I divide it by 1/2. Okay? Because x squared dividing by 1/2 means I multiply by the reciprocal of 1/2, which is 2 over 1, which is 2x squared. So this, I can rewrite it like this. Okay? So to bring this 2 down, I'm going to undo that reciprocal property of fractions. And then this becomes this. 1/2. And then so I make it look like an ellipse. This is just a 1. That way it starts kind of having that form of the ellipse. Yeah, no.
Would it also work if you divided everything by 2?
If you divide it. Oh, yeah, I guess you're right. Yeah, you're right. Let's see.
So then it would just be like k over 2 equals.
I like that better. I'm going to do that instead. Okay?
Okay.
I think the textbook will do that, but let's just see where this takes. It's going to give you the same result.
Okay.
Let's say we divided everything by 2. 2, 2, 2. So 2, 2. Nope, just cancel, right? 1 and then 2. Ah, okay, yep. But what do we want our ellipse equation to always equal? 1. You're going to want it to equal 1. So now what do we have to do? Multiply by the reciprocal, everything by the reciprocal, which is 2 over k. So multiply this by 2 over k, multiply this by, that 2 still shut.
Yeah.
I think better to divide by 2.
Let's do that. Let's divide everything by k over 2. That way we don't want to bring anything up there. Okay, so this becomes a 1. Here, you got x squared over 1 divided by k over 2, right? So I'm going to multiply it by this weird reciprocal, which is 1 over k over 2. Is that okay? Remember we did that earlier? When I was dividing this fraction by 1 minus k, this really just ends up multiplying with 4. I'm dividing 1 by k over 2. These two just end up multiplying. So it gives me x squared over k over 2. Plus, these will just end up multiplying. So 2k over 2, which is just k, right? Yeah. It'll just be k. Or no? Oh, I fucked up. There you go. There you go. That's better. I messed up. So these two multiply and the twos cancel. There you go. That makes more sense. Okay, sorry about that. Cool. Okay. Whew. What is the graph of this going to look like? It's going to be an ellipse. And in which direction is it going to stretch longer? In the y direction, right? Because this denominator is bigger than this denominator. Okay. Here's where it gets weird. When k is 0, can k be 0? It can't be because we divided it off, right? But in the original equation, can it be 0? If it is 0, what has to be true about x and y? Which is what we saw. It was just the origin. Remember the xy plane on the paraboloid was just tipping, it was cusping that point. So it's z. But as k gets bigger, the ellipse is going to get bigger, but it's longer in the y direction. So that we saw that it was kind of doing this. Like that. Okay. It's getting longer that way. If you look at your sheet, oh wait, not yet, not yet. Don't look at your sheet yet. We'll get there in a little bit. Okay, once you get the three traces and you have like an idea of how the traces look like and how they look like as k is changing, which is one of the hard parts, you're gonna put all this together, which is where the artistic skills can get pretty rough. Okay. Which one do you guys want to start with? This one? You guys pick. Maybe you don't care which one. Okay, let's do x equals k. So remember, this is the x-axis, right? And then we were thinking of the YZ plane. So you're thinking of this plane right here on the board, literally on the board. As x got larger, what was happening to that plane? It was coming towards us, right? When x is 0, we saw that we had a wider parabola like that. But as x was getting closer to 1, let's say x is 1, this parabola was higher, right? But it was higher, but it was also in front, where x equals 1. This is where it's going to be hard to draw. So it would be something like this, but like in front of it. Okay? And then what happened as x kept getting bigger? It got higher. Maybe I exaggerated how high it got. It's like a little bit higher like that, right? And then the parabolas are just going to keep getting higher, but they're going to keep getting more in front of each other. Okay? I'm not going to draw the back ones. And then the back ones also get higher, but they're now going in towards the board, like behind it. Okay? Let's do these ones. I'm going to change colors. See this red work? Oof. Okay. Now we're going to look at the XZ plane. That's this one. It's kind of like this. And the parabola, when y is equal to 0, sorry, when y was equal to 0, that was this parabola right here at the origin. So, but now the parabola isn't facing us, it's kind of slanted in the direction of the XZ plane. So it's going to be something kind of like, and it's skinnier. So it's going to be something kind of like this, but it's like slanted. It's going to be hard. Okay. Let's increase y equaling k so that these red parabolas are going this way towards the positive y direction. What happens to the parabolas? As y is increasing, what happens to them? They go up, right? So as y is increasing, they're going to go in front of each other, but they're going up. Like that. They're in front of each other. Okay? And then the last one is our ellipses. When k was 0, that meant z was 0. That just was the point. Amen. We do agree. That was just the point. What happened when z was increasing? The parabolas were getting wider, right? But what was happening to the parabolas in 3D though? Sorry, the ellipses. They were getting larger, but they were getting stacked on top of each other. So they were going like this. And they were wider in the y direction, right? So they were doing kind of like something like this. Like that. We didn't talk about this part. What happens if z is negative, what sign would this fraction be if z is negative, if k is negative? Something positive over a negative is something positive over a negative. Can two negatives add to one positive one? No. So in this case, that tells you that this is undefined if z is negative. So there is no graph. Okay. So note, if z equaling k is negative, we have no traces. We have no traces. Which means there's nothing under this. Where z goes negative, there's nothing. So then you're gonna put the pictures together, and then you'll see here, you're gonna look at your sheet here. What kind of graph do we have? What's the name of it? We have an elliptic paraboloid. Like that. Okay, when you put it together. This elliptic paraboloid opens in the z direction because of all the traces we did. But on the homework, they might change this problem, and then they'll write this, y equaling 2z squared plus y squared. You'll look at your handout and you're going to freak out. You're going to say, oh crap, I don't have that form here. I only have z equaling x squared plus y squared. So then that's where you got to use a little bit of the traces. And you'll see that in this case, the paraboloid will open in the y direction. Okay? It'll open in the y direction. But with practice, you'll do that. Questions? It's hella visual, right? It's very visual. Because it's very visual, we're going to wait a little bit on the algebra, and I'm going to have you guys with groups just practice the visual, because that's the hard part. Okay, it's visualizing. So the same kind of groups that you guys bundle up with. The first problem, I give you a quadric surface, and then just from the surface, I want you guys, without algebra, just try to sketch what the traces would look like on the xz plane, yz plane, and xy plane. Okay, without the algebra, you're basically just going to jump to this here. You want to train your brain on like the plane intersecting the surface. The second problem is the opposite. I give you traces, and I want you guys to try to see what's the possible surface that can correspond to those traces. Okay? So it's a very visual exercise. 1, 2, 3, 4, 5. 4. If you have like color pens or anything that color coordination, this will help. If not, it's all good. Let's see. So what do you think you for? I don't mean just not get color. I think over here. It's gonna be like there's a variable. He has 2 y. You're like a lot of you guys just kind of check in, you know what? I think he can see your y. Does anyone have exercise step 4 that they want to hand in?
Oh, all the bases are. No matter what three game it looks like this one. Like a skin.
This is what we're
I'm gonna do the traces for all three coordinates, okay? If it's the ellipse, try to show me which side's longer, on which axis it's longer. Like here, we said it was longer in the y direction. Just show that in your drawings. Yeah, what's up? Oh, like if it was z squared.
What you wrote in slide, y equals two z squared plus y squared. Oh, that looks like, yeah, like another y, so I have to do that, like a different three.
Oh, like if I had something like that,
Yeah.
it won't look like this.
Mm.
It changes completely.
We're gonna have to.
No,
Oh, okay.
nope. Yeah, the class will keep it so that it's in general these ones. The homework might have you play a little bit more with them in this section, but down the line, they're going to be pretty much just this.
Oh, shit, you're doing it. I'm doing it like this. Didn't show this. You're doing it. This should be, I need to really get a.
Yeah.
Get my.
The X, Y point is down here too, let me have it.
Keep in mind the traces will be parabolas, circles, ellipses, hyperbolas, lines. That's pretty much it for these ones, these circles.
I was thinking like, honestly, it would be like. This one right here. Kind of going like that. Like, this would be the ones you right. So if.
Walk around.
Yeah, exit, yeah.
Oh.
This plan is coming out of that one.
Okay, why is it being like going after that?
Yeah. Please view it from the top.
Got it. So that would.
X, Y.
Like
the X, Y.
You would say-
Like an X, Y.
Yeah, you would label, for example,
With the ellipse.
label it k equaling 0.
Your first.
Okay.
So like when you draw your,
Like there. I think
when you draw the faces, just what do you think the face is?
Yeah, I think we're just going to use her.
Well, then,
Like, is there?
Correct.
And I do want to label something, so if you're looking at the angle, you're like, you know, like this, you have.
Once it does hit, what are the shapes?
So.
Now that the dot is.
Oh, yeah.
So you would say like, yeah, the k equals. Yeah.
Yeah.
Just to know.
It's on like the parabola.
Yeah, that's a good point. The y axis?
Yes.
Yeah, the right.
Yeah.
Mine. Oh, this one? You might want to start. What best?
They don't though. If they were to look the same, it's not a base speeder. So some of them is swimmer would be wider. And then they're actually gonna keep it. I think two of them would be the same. I think two of them are the same. And then it's only the 5 feet that's like the rounder one. That's the spot right. I'm looking at the top. It's like a big circle here, and it keeps getting smaller. I thought the X would be like big house.
You know, I think it's.
Yeah, I think it's when you're looking at it like straight this way, right? Having two circles perfectly on top of each other, but you only can. This is
Just driving forward me and
how many traces?
If you haven't yet, can I just have you guys share your work with your classmates? Just to see if your guys look great, look similar. Like maybe chat about something that's pretty challenging. Yeah.
That was going on.
I was wondering why. Give you guys a few more minutes. It's all good if you didn't finish, okay? Remember, this is just additional practice. All good, no finish. Here, a few more minutes.
Yes. Was it, yeah,
Okay, you're probably gonna want to use that one, number 2. Oh, I know it's gonna look like. You put this one in, I think it is this, but. Also, keep in mind inspirations. Yeah, it's gonna open, hold on. No, it's gonna open the browser, the link, the sign. It's going like this. But again. Oh, I like my use of the. This one has a cross. With a cross, exactly. But when you like. I'm grabbing Oh, so it was just like. That one because look, if X equals it's this one. Okay. No, it's this one. Let's see, was D equals 0. This is parentheses.
I'm trouble visualizing, I see.
Next slide. Actually, oh, yeah, yeah.
That one's like seven.
No, it would be. So that you can take. Is it the same thing?
Oh,
That's what I'm like, that's you.
and it could be
It's like,
it's
you know, one of them has to be like.
A equals 0, so X equals 0, it's not.
Oh, yeah, I would.
Yeah, like, you're right. Yeah. We'll have a whole other guy.
But it.
It's gonna happen.
So when y is 0. What being is this?
I like it. That's very.
Yeah, that's right. And it's. Why has that to be some kind of positive start number? Let's say that. I swear. Because what's the point of the yeah. That's literally shooting. So those circles or ellipses, you can't really tell, or center. Okay. Oh, it can be like gravel.
It's all learning. And then I was getting somewhere. And then I got like a top out. Got like a thing. Yeah.
My brain.
Okay.
You guys, one more minute, we're gonna move on. One more minute, it's all good, it's 1 minute. Solutions will be posted on Canvas.
Let me clarify that. Guys, guys, real quick, real quick, real quick. Number two, your surface should have both of these as the trace. Just in case somebody was, because some people are drawing a surface for this trace and a different surface for this trace. No, your one surface should have both of these as possible traces. Okay? All right, I'm gonna let's go on a break and we're gonna resume at 2:05. You can keep working, that's fine. So resume at 2:05. All right, so I hope that worksheet helped kind of practice, have you practice some of the visual stuff? I believe it should be a cone. Because I think when x, what was it, z equaling k? Let's see. I believe it should be a cone because when z equals k, equals 0, you're getting those two lines.
Numbers for k or swap around them. If it goes from hyperbola to straight lines, then that bit different.
Oh, yeah. No, I think it's, yeah, I think it's the hyperboloid of one sheet or something like that. Yeah. Hyperboloid of one sheet, yeah, should be that one. All right, guys, we're gonna move on. We're still in this section though. So you just practiced the visual. Now we gotta practice the algebra part too, okay? The fun stuff. Before I do that though, as you saw, some of the traces are hyperbolas. So let me just do a super short review of hyperbolas and some funky stuff that will happen with traces. So, quick hyperbola review. So let's say we just want to start with x squared over 4 minus y squared over 9 equals 1. And let's remember how we start graphing, okay? So kind of similar to ellipses. This isn't, I forgot the form, but it's one of the general standard forms of hyperbolas. But instead of, doing an ellipse, you still use these values. But what you do is you make a little box out of them, a little rectangle. Let me remind you how this works. So you're gonna you take the square root of these values below, because normally it's like a squared and b squared. And in this case, a would be what? 2. So you go 2 units. You go 2 units in the x direction. So it'd be right here at 2 and -2. Right here, and right here. And then for y, b would be 3 -3. So you would go to -3 and 3. And what you do is you draw a little rectangular box so that it goes up as high as negative and positive 3 and side to side -2 to positive 2. Make a little rectangular box. Okay, I know it's been a minute since you get it. And then you draw diagonal lines that cross the corners of this diagonal box. I'm not going to expect you to do all this, by the way, okay? It's fine. Asymptotes. Yeah, you'll see why. Because this is not the graph. You use this box with these asymptotes. If you have if you have the x squared that's positive versus if you have the y squared that's positive. Okay. The variable that's the positive one, that's the direction the hyperbola is open to. So in this case, x is a positive and y is the negative. So the hyperbolas are going to open towards the x-axis, like this. If I was to instead write y squared over 4 minus x squared over 4, then the hyperbola is open towards the y. But the box would still be the same. Or no, it wouldn't. It wouldn't. If I swap these two fractions, sorry. Okay, super fast review. I call it. But I want to play with decimals for a little bit. I'll leave that there so you guys can see it.
Hyperbolas are the things like sine H and cosine H, that stuff.
The cosine and sinh,
Yeah.
those are not, they're I forgot what they're called, but they're a little different.
So, yeah.
Yeah. Okay, so let me let k be 0 right now. Okay, see when k is 0, these hyperbolas are the ones that we just drew right here. Okay, yes. They both cross through the origin, so the y-intercept is 0, and then the slope would be whatever this b value is over whatever this a value is. So it's b over a and negative b over a. Y equals negative b over ax. So it'll be linear equations, which I'm not going to have you guys do, okay? But I want you guys to notice this. If I would have made the x negative and this a plus, notice the hyperbola is now open towards the y direction. Okay? Okay. But as you saw right now with these examples, it gets tricky if instead of just a 1, I have a 1 minus k. Or a k squared, whatever the thing is. Okay? That's where it gets tricky. Because now from here, I have to, what do I have to do to get this to be a 1? I divide everything by 1 minus k, and what happens with this denominator and the 1 minus k? They multiply. So it ends up becoming this. I divide by 1 minus k. Okay? Before I do that though, what happens before I divided it? What happens if k equals 1? It becomes 0, right? Let me just do that over here. So then you end up with something like this. Equals 0. Move this to this side. Square root both sides. And then I'm going to get plus or minus y over 3. That's or actually let me do it this way. Plus or minus in this direction, in this side. Multiply the 3 to both sides. And what is this? What is the graph of these numbers? 2 lines, right? That are just going to cross to the same, or they're going to cross to the origin, but they have slopes that are positive, negative. And those are not quite, no. Those are literally the hyperbolas, but they're not hyperbolas in this case. So let me show you guys. Let's have k get closer to 1. And then boop. That's those lines. The slope is, what do we say? 1, 2, 3 over 2. That's those right there. Those are the traces. So kind of like the handout, you guys see those 2 lines? That's kind of what we have. Okay. Okay, but here's where it gets weird. So I divided by k. Here k can be 1, but originally before I divided it, it could be 1, right? If k is bigger than 1. A is bigger than 1. What kind of number do you have? Positive or negative? If it's, let's say, 5, you're gonna have a negative, right? So originally this was negative, but now it'll turn positive. And originally this was positive, and now it'll turn. So what do you think happens hyperbola to the hyperbolas? They swap, yeah. So originally they were opening in the x direction, but once k gets bigger than 1, they swap. Okay? That's what I wanted to show you, because that's where it's really weird. Okay? So they go like that, and then bloop, they'll swap like that. So I just wanted to show you that. Those are the more complicated examples where that's going to happen. Okay? And that tends to happen with the hyperboloid hyperbolic paraboloid. Okay, where because of that saddle, the hyperbolas are facing in one direction and then they swap in a different direction. Okay. Let me see there. Yeah. Okay. So I want to show you that. And we'll do a little quick review on hyperbolas. Okay. What time is it? Is that now? Okay, so I have. Let's see, what do I have? I have one practice example that you're going to do by hand now. And then I have 2 other ones that will be in my notes that we're not going to have time to do, but they'll be in my notes. Okay. So the one that I would like you guys to do now. This one's by hand. So you're going to start by doing the traces the way we were doing it with this example, where we substituted the variable with the constant. Also, use this handout to kind of give you an idea of what the shape should look like. Okay, just to kind of give you some intuition. All right, so use traces to help you sketch the surface of y squared equals x squared plus z squared. So what you're going to want to do is you're going to want to make your traces. Do this guy, do this guy, and then do this guy. Just like we did here, when z was equal to k, I plugged in k in for z. And then then you're going to help yourself see what type of trace you have. You'll have ellipses, hyperbolas, parabolas. That's where it gets kind of hard, okay? So that's what I want to do this practice. So try it out with your group. Oops. And then let's see, what should I put this? Let me just remind you. So for ellipses, usually you have something. I'm gonna write it all in X, Y. Usually it looks like this. For hyperbolas, it's similar. Remember, if it's not equal to 1, and it's either two squares adding, and it's not equal to 1, divide it so that it turns into a 1. If you end up with one of the variables that is not squared, then you probably end up with a parabola, okay? You isolate the variable that's not squared. But if all the variables are squared, then you can't have a parabola, so then you want to move all the squared variables to one side. Okay, here, I'll do the first one with you guys. So watch. You got this right here, right? Is there any way I can change it so that it looks like this in this way? No, because all the variables are squared, right? So then, since all the variables are squared, let me bring all the variables to one side. So which one do I have to move? Z. What do I have to do? You got to subtract it. So now I have a constant here. I subtract it. So which of these three might it be? Probably going to be a hyperbola, and therefore I want them to equal 1. So then I'm going to divide everything by k squared. So that this turns into a 1. And so yes, it's going to be hyperbola. So remember that if it depends on the variable that's positive. So here on the y, remember this is x equal k on the yz plane. Y is positive, so they're going to open in the y direction. Well, let's see. So before I divided it, right? Before you divided it, it's that weird 0 case. Yeah. So if k equals 0, kind of like you did here. You're gonna move the z over here. It's gonna be very similar to this. You're gonna end up with 2 lines, exactly. So then if k gets bigger, positive or negative, then your hyperbolas, should be like moving that. Because this box is getting wider.
Negative.
For the third one, we don't have to draw it in YCK.
Say again?
For the third one, we have to draw it in YCK.
Sorry.
Only Y. Okay.
On the Y.
We don't have to, in the YCK thing, we don't have to draw that one.
Oh, I'm not done. This is just the traces. Yeah. So your first trace should be hyperbolas that open in the Y direction. And then when K is zero, it's kind of similar to this situation. You're gonna end up with two lines. And then similar with this one here. It's hyperbolas opening in the Y direction. When K is zero, you end up with two lines. But they're opening in the Y direction. In this case, they don't switch like we did in the decimals example because the denominator with K will never, it's always positive. Here, what is this, guys? It's going to be an ellipse with both the axes being the same, so it's really just a circle. So when K is 0, X and Z both have to be 0, so you get a point. Circle like that. So if you put all this together, let's see. When Y is shifting, so when the XZ plane is shifting, you're getting a bunch of circles. A bunch of circles. When Y increases in the positive direction, so you have a point, and then it's just a bunch of circles. But when Y is negative, this is just being squared, so you get the same circles going in the other direction. That. And then when X is something like a positive, you're going to get these hyperbolas. So what's gonna end up happening is you get a cone. Okay. Where, for example, when x is increasing towards you, you end up with these hyperbolas like this. Opening in the y direction. Opening that way. Those are the tricky ones. This is for the x equals k. For the y equals k. Now it's going, let's see, when y equals k. Did I do this in the right way? Wait, I think I did this. Yeah, no, sorry. You mean when z equals k? No? When y equals k, it's the circles. When x equals k coming towards us, it's slicing it at these hyperbolas. Right here. It's hard to see. Yeah. And when z equals k going up, you're getting these hyperbolas like right here. I mean, I'm running out of colors. You get these guys right here. That. That's when z is rising. The hyperbolas are going away from each other. So when your z is 0, you get these lines right here. It's hard to see them, guys. It's like those lines crossing right here, or these ones. I know. This kind of visual thinking you're going to do a lot in this class, especially also in chapter 14. Okay? So, it's your first day doing this, so it's okay to feel a little uncomfortable because it's like your brain's probably, it's thinking some kind of way that it's probably never had to think before. Okay? All right. What is it? 2:30? So that's it for chapter 12. Your exam goes up to here, up to this section. Okay? The exam 1 goes up to 12.6 quadratic surface. Yeah. Maybe. We'll see. Maybe some problems like the handout that I gave you. Who knows? Okay. But when you get to chapter 16, which is 15, which is integration, you are gonna intersect stuff like this with like a paraboloid. So you'll do a cone, and then you'll put a paraboloid on top of it. And you're gonna have to find the volume of the stuff inside. So that's why you're gonna go extreme with this kind of drawing stuff. Okay. You'll find the integration chapter, the hardest part is setting up the integral. Once you set it up, then it's Calc 2. Okay. Okay. We're gonna have to move on. All right. Now this is all about surfaces. Chapter 13 is all about something called the space curve, which sounds kind of cool. I like the name. On my notes, like I said, I have 2 other problems like this one. Okay, so you guys can get more examples. All right, chapter 13. So space curves and vector function. A lot of calculus is in this section. And sorry, in this chapter. We're going to be doing maybe not so much today. You're going to have to review integration techniques in this chapter, differentiation rules, all that good stuff. I don't think we've done any calculus yet. Right? It's all been geometry. Well, I guess parametric equations, but that's not really calculus. That's just more geometry. Okay. So let's start by talking about what a space curve is. So consider a curve in 3-dimensional space R3 whose points we've kind of been doing this with lines, whose points x, y, z are parameterized by t, where, let's say, we're going to have x be parameterized by the cosine function, so cosine t. Y is going to be parameterized by sine t. And z will just be t. You go back to your wonderful moments of Calc 2. It was good times. Z didn't exist in Calc 2. So in the XY plane, you guys remember what this was parameterizing? It was parameterizing a circle. And you're thinking of t as the angle. Okay. So remember that happened because of what you learned about polar coordinates. Similar to polar coordinates, where you learned that x was given by r cosine theta and y was given by r sine theta. So what's the radius of the circle that it's parameterizing on the xy plane? 1. But then we got this t business going on. Okay. So let me show you guys what ends up happening. Down. Let me double check that I have that ready for you. Not this one. Okay. Okay. Oops. Here's a circle. Pretty little circle. The red axis is x, the green axis is y. Okay. Right now it's saying s. Think of s as like the t here, the angle. Okay. So it starts where x is equal to 1, right? And then you guys saw that when, oh crap. Something funky is happening. Okay. There we go. As x increases, it goes around the circle, right? In a counterclockwise direction. Okay. So there's this point with this coordinate, right? But now z is involved. So this is what's going to end up happening. What do you think will happen? Yeah, it's like a circle, but it's rising. Right? Because as the angle is increasing, t, z is the value of that angle. So we end up with that. Okay. And so here it's decreasing. Let me have it bounce back. So it's increasing. So basically, if you think about it, what you've been doing in Calc 2 is you've been doing this, but now there's just a different dimension to it. Okay. And so yes, it's this circle that's just kind of slow down. That's just kind of going around. But now it's going around upwards like this as t gets bigger, z gets bigger. As t gets smaller, z gets smaller. Okay? And you kind of been doing this with lines, but remember there's that magical wand. Okay, this is the magical wand that's drawing, which is the terminal point of a vector. Okay, so what we're going to do for curves is in Calc 2, you guys use parametric equations, but in this class, we're going to have vectors called vector functions that now you plug in a t value and it'll give you a position vector where the terminal point is the point that's drawing the curve. Okay, that's kind of what we're going to be doing. Let's see. Let me give you different examples. Oh, dang it. Hold on. Is it going to ask me to log in? Hold on. No, okay. Okay, so watch. Found this toolbar here. So this is just talking about this is a curve we were looking at. Okay. Here's an example of like a type of application where that curve shows up. Look at how complicated the x, the y, and the z now are parameterized. a lot more complicated than the other one. So I want to show you guys. This is the curve that it's sketching out. As t is increasing, notice the orientation of the points moving through the curve. Okay. This is the one that we just looked at. We already saw that one, so let me go to the next one. There's this one here. Okay. Notice the oscillation because all three of the coordinates are parameterized using a trig function. And trig functions oscillate, or at least cosine, sine, and tangent. Okay. This one's gnarly. Okay. It's going too fast. It's like, there we go. But notice that this is where t starts at the time, right? And it's drawing the curve. So what's going to happen is that we are going to have the function describing this to be a vector. But in terms of the graph, you ignore the vector in terms of what's actually being graphed out. The graph is the curve. Cool? Okay. What is this part? Oh, yeah. It says, when would I use this? So it says in nuclear reactor, scientists use equipment to produce energy from nuclear fission. Nuclear fission depends on finding exact paths of nuclear particles through space. Such paths can be modeled using vector valued functions, which we're going to look at in a little bit. Biologists will sometimes track birds during migration to find their migration route and destination. The set of points that represent the bird's location over time is a vector valued function that approximate the space curve. And then a little bit more. Okay. When facing a strong crosswind, an archer must consider distance from the target, vertical aim, and horizontal aim. Due to the crosswind, the arrow's flight path must be modeled with a curve in space instead of a curve in the plane. Okay. So here are just some examples of applications. Okay, so let's see how we're going to do this with some of our math tools here. Now, stop sharing the screen. Okay. All right, so let's define first this thing between space and vector functions. So, at the beginning of the chapter, there are some definitions we gotta go through. So we're gonna say a space curve C is the set of points X, Y, Z, where X is going to equal some function f of t, Y will equal some function g of t, and Z will equal some function we're going to call h of t. When we're dealing with R3, we call them space curve. Okay? When we're dealing with 2 dimensions in R2, they're called plane curve. Where they're just curves that are being drawn in plane. And then your textbook is going to call F, G, and T here. So F, G, H are the parametric equations. Function. So this tells you the points on the curve. But now we're going to define the vector that's drawn. Definition. We're going to call that a vector function. It's your first function that I think this is the first time you guys see a function that inputs a real number and does not output anything. I think everything you've dealt with is done, except that you just ignore that. But a vector function is a function. We're going to say R with a little vector arrow, whose domain D. I want you guys have seen this notation. Is a subset. Have you guys seen that notation? Okay. Of the real numbers, meaning it's not, it might not be all the real numbers, but it's some kind of smaller set thing. That's kind of what this notation, subset. And its range R is a subset of three-dimensional vectors. Remember in the notes when we were talking about vectors, Vn represented the set of n-dimensional vectors. So this is V. And this is just saying the range of this function outputs some type of three-dimensional vectors, not all of them, but some of them. Where R of t inputs a real number from the domain, and it'll output a three-dimensional vector given by the parametric functions. In the first page. When dealing with a vector function, instead of calling it parametric functions, your textbook will also call them the component functions. Since they're the components of the vector. And so like you guys saw on the little videos there, in 3D space, you have your curve just kind of, it'll be oriented in a particular direction. So let's say the points are moving in this direction. It's a roller coaster that's going in this direction. You have some points. This is C. Yeah, thank you. This is C.
No, you say it's
Z?
Yeah.
This is the Z axis. Yeah. Sorry, that's my Z. So we're going to have a vector, that little one that I was showing you, that is the output of your vector function. So t, think of it like time. At a particular time, your vector is positioned somewhere. It's not moving. As t moves, that position vector will move. And the tip of it draws the space curve. It draws the space curve so that the point is given by the parametric equations. And so as t is moving, the direction that it draws out the space curve is what's the orientation of the curve. Okay. So your value t is going to control the orientation. Which one? F of t, g of t, h of t. Oh, this one is the vector. Oh, yeah. So this chapter gets funky. It's new. It's like usually you output a number, right? Here you output a vector. The vector is the output. So that its terminal point corresponds to the point given by the parametric equations. That's why these are really significant. So when it comes to the domain of a vector function, now you got to deal with three functions at the same time. Okay. So the domain of a vector function R is going to be the intersection of the domains of all its component functions. You got to make sure that the domain works for all of them, not just for a few of them. It has to be defined for all three functions. So it's going to be the intersection of both of them. So you'll have a homework problem, for example, that looks something like this. It'll say find the domain of your vector function R, where let's say the functions are t cubed, ln of 3 minus t, and the square root of t. Okay. So because we need to see the intersection, I need to find the domain of each one. Okay. And the domain should be real numbers. So it's going to be interval notation that you guys have been using in calculus. So let's start with this one. What's the domain of this one? An interval notation. What can't this be? It can't be negative, right? So t has to be greater than or equal to 0. In interval notation, that means it's going to be from 0, including 0 to infinity, right? Okay. This one you probably don't remember, but what kind of values can you not have inside a log? Zeros or negatives. So what must the inside be? Has to be positive. So I'm going to let the inside be positive and solve for t. Move the t to this side. So what does that tell me about my domain? It has to be less than 3. Including 3? No, right? Because I don't want it to be 0. So then it's going to be negative infinity to 3, but everything before that. And then what about this guy? That's everything. Everything's gained for that one. So my recommendation is you draw a number line. Here's 0, here's 3, and then kind of conclude the intersection. This one says it's everything. This one says it's everything up towards 3, but not including 3. And then this one says everything from 0, including 0, on. So then what would be the intersection of all three things? Yep. It has to be 0. I could include 0, but then it goes up to 3. I just can't include the 3. Okay. And so this is the domain of the vector function. Okay. Yeah, it's not too crazy. It's a little calc one. Throwback. Hey, today's Throwback Thursday. No. Or is it Throwback Tuesday? No, Throwback Thursday. Okay. Yeah. Okay. Questions? Limits. Little calc. Okay. Limits. It's gonna get funky. Limits, baby. All right, this is how we're gonna define the limit for these weird vector functions. For a vector function, let's say R, and let's say its component functions are f of t, g of t, and h of t. Right, so you got a vector. You can use some space curve. Its limit at t equals a is, this is how we're going to write it. The limit as t approaches some value of a of my vector function turns out, because remember, if you guys remember the limits, it just means t is getting close to a, right? So what you're looking at is you're looking at the vector, but you're basically looking at what point is it approaching. So I need to know the behavior of what f of t is approaching, g of t is approaching, and h of t is approaching as t gets closer to a. So then the way it's going to end up working is you just take the limit of each of those functions to tell you what x component it's approaching, what y component it's approaching, and what z component it's approaching. Assuming all three of these exist. That's important. So, assuming all limits exist. So let's look at this function. Let me slow down. And let's look at a limit, but let's have a value of a be in its domain here, or maybe at the ends. Let's say it's defined at 0, it's not defined at 3, but remember, this doesn't have to be in the domain, right? So let's see what this function is approaching as you approach 0 from the right, and as you approach 0 from the left. It's funky, okay, but let's see. So let's figure out what is the limit as t approaches 0. What did I say? From the right of r of t, given by this function here. Or actually, let me write it like this. T cubed, sorry, t cubed ln of 3 minus t and the square root of 8. Okay. So what you're going to do, we're going to take the limit of each as t is approaching 0 from the right. What's the limit of this as t is approaching 0 from the right? 0. So 0. It's a direct substitution, right? Here, can I plug in 0 for t? Yeah. Yep, it's in the domain. So we get what? ln of 3. And then here, 0 is also in the domain. So we just get 0? 0. Did I look up? Yeah, ln of 3, guys, is approximately 1.1. What the hell does that answer mean? Okay. Remember, this vector function is one of these, right? It's a vector. So it's like moving. But as t is approaching 0 from the right, it's moving and it's approaching this vector with these components. 0, about 1.10. So now your limit isn't a value, it's a vector that it's approaching. I'm going to show you all this, but Let's try to grasp it. Now let's see what happens though if I approach 3 from the left. Let's do that one. So let's approach 3 from the left. Help me out here. So can I just plug in 3 here? Yep. What's that? 27? 27. Ooh, here's where it's going to get weird. Yeah, what happens to ln as the inside approaches 0? The graph of ln goes like that, right? So as it's approaching 0, the y values would be approaching going down. So the y values are they don't have a limit, they're approaching negative infinity. Okay. So it doesn't exist, yeah. Here I can plug in 3 and I get square root of 3. But it's this guy that gives us the issue here. Okay. So D and E, limit does not exist. There's no vector that it's approaching. What does that even mean? Like, what does that mean visually? Let me show you. Yeah. Yeah. So as t gets closer and closer to 3, the y coordinate just keeps shooting towards the negative direction. Let's see exactly how that's happening. Is it this one? I had one ready for you guys. Nope. Here it is. Okay. So this black curve here is the graph of r of t. The graph of this vector function. The space curve. Okay? Of this vector function. That's this black curve right here. Just kidding. There it is. This space curve right here. Okay? As t is increasing, look, there's a vector that's drawing it. That little green vector right there. That's the vector that's drawing it. Okay. As t approaches 0 from the right, you guys see how the vector is moving? But if you guys think about it, it's an infinite number of vectors that are the outputs. Every time t changes, it's a different vector. But it just looks continuous. But it's an infinite different vectors that are being outputted. Okay? But let's see, as t is approaching 0, as t approaches 0, it approaches that vector right there. This green one. Can you guys see the green vector? Let me remove this. That green vector right there. What are the components of that vector? X is 0, which is true. It's x is 0, z is 0. But what's y? It's about 1.1. There it is. That's the limit vector. Okay. But now let's see what's happening as it's approaching negative 3 here. So it goes, and GeoGebra shows that it stops, but look, it actually keeps going. Okay. But what I want you guys to notice is the x value is this really big x value. Let me go like this. Hold on. Let me move it to 27. How do I do that again? Okay, here we go. There you go. That looks more like the curve now. It was missing some of it. So it keeps going. Oh, it went so fast. Hold on, let me go like this. Let's go 2.5 to 3. Hold on. Come on. Okay, maybe that's too slow. So it's going. And then it's just gonna it's gonna shoot out. But it just goes really fast, okay? But look, it shoots out, but it seems to kind of go this way. In terms of x, notice that it seems to stay about a value of 27. And in terms of z, notice that it seems to stay at a value, which I think is like 1.7-ish or something. Okay, which is right here. But in terms of y, it just shoots towards negative infinity. So there is no limit. It doesn't end up at a limit. It just keeps shooting down. But that's why these end up having a limit, but this one doesn't. But because you don't end up with a vector, there is no limit. So you would say there's no. Okay. Sorry about that. You're like, you guys were giving me weird looks too. What curve is he talking about? 10 minutes? Perfect. We'll end with this. So as I was showing you guys some examples, the curves can get pretty gnarly. But sometimes there are some hints to kind of give you an idea of what the curve should look like. Screen. So let's see how we would do that. Let's see, sketching. Space good. In general, it's pretty challenging, but it's some that we can kind of grasp and get an idea for it. So the kind of the idea behind this is we take one function at a time. So for example, here for this function, what are things we know about the outputs of this function? They're all positive. Okay. Say it again. Yeah, they're non-negative, right? What about this one here? They're going to be all, yeah, all numbers, but we also saw some behaviors of them, right? We saw some behaviors of them. And then this one here could also be all kinds of them. Doesn't help us a lot, but it does tell you that z, for example, the curve is never under the xy plane. The z will always have to be non-negative. And I don't even know the curves, okay? But you're going to use your knowledge of trig here to help you out. So I'm going to practice, but we're going to kind of do this together. So what you're going to want to do is use your knowledge of polar coordinates. That's what's going to be very helpful. To help you analyze what each coordinate is doing or behaving, what do you say, doing for the curve. And the curve is given by this guy. Cosine 2t, cosine t, and sin t. So we'll kind of put our brains together and see maybe like what might happen. So it's cosine 2t, cosine t, and sine t. So one thing you're going to want to use is if two coordinates are of the form A cosine B t and A sine B t, you can use polar coordinates to deduce circular motion.
there'll be circular motion in the YZ.
Exactly. So these two both have kind of the same value in front, which is 1, and the t is both being multiplied by 1. So notice that on the x, sorry, what did you say, on the y z plane, those are circular, right? If you look at that in the YZ plane, what's the radius of that circle? It'd be 1, like we did earlier, right? With the other part, but in this case, it's in the YZ. So yes, let's write some of that stuff next. So I look at this function, and first I try to identify, see if I can do something like this. Yes, so this tells me y and z are in polar coordinates. And so they, where the radius would be 1 in this case. I know that because cosine and sine, what's the maximum positive value between sine and cosine? The smallest. Yeah, so now I know my space curve for x's, for y's and z's have to be between -1 and 1. Okay, so now I know that y has to be between -1 and 1. And z has to be between -1. Since cosine and sine are both between -1. And so on the YZ plane, I know that there should be some circular motion counterclockwise of radius 1. Well, usually if it's in polar coordinates, and like if I label this the y-axis, that's what matters. This is like the cosine here. The first coordinate here would be the cosine function, and the second coordinate would be the sine. If these were swapped, yeah, that's a little different. Or I can label this the z-axis and this the y-axis. Okay, for this guy here, it doesn't correspond to another coordinate, so I can't think of it as like polar coordinates in this case, but it's still the cosine function, right? What's the maximum and minimum? So then this tells me that x is also between -1 and 1. And what's the behavior of cosine functions in terms of how they change? They're periodic. And so it's going to oscillate between -1 and 1. It's going to oscillate between -1 and 1. In general, this is hard, okay? This is a hard thing to do, but you can kind of piece together some behavior of the space curve. So let's see if we can kind of put over time. Okay, right. Okay. So I know on the YZ plane, if I ignore x, the points move in a circular motion on the YZ plane. Okay. And they're going to move between 1 and -1. They're going to move between 1 and -1. And then you might have to, let's plug in some values here for t. If t is 0, what's x, y, and z? Cosine of 0? 1, 1, 0. So we're kind of like 1, 1, 0. So it's somewhere floating in space right here. Okay. After this, though, we know that in terms of the YZ, it needs to move like this. It needs to move like that. That has to happen. Okay. You guys see how this is 2t though? So does it take 2 pi to oscillate between -1 and 1? Yeah. From 0 to from 0 to pi, from 0 to 2 pi, that's right here, right? So it's not going to take a whole 2 pi units of that. Okay? When t is, let's see, we got, when t is pi over 2, what would this be? Yeah, cosine, let's see, we got cosine 2 times negative pi over 2, that's -1, right? Cosine pi. So x would be -1. At pi, though, we know that in terms of the yz, it's up here, right? Because it's following the same as polar that you guys know. It's just this x is throwing us off. So now we know it's here, but x is -1. So it's like it's back here somewhere. Okay, and we know it has to go in a circular motion. What happens when t is pi? What's cosine of 2 pi? 1, right? So, but now we're here at pi. So now we're here, but x is 1 again, so it went here. It's like it went 1, but now the circle has been rotated like this. So let's see so far what's happened. We know it's going in a circular motion, and we know x oscillates like this between 1 and -1. Okay, these points are towards you, this point is behind you, behind the board. So it's kind of, we have like this circle that's kind of folding in like this. Let me do this better here. It's like shit can I do? It's like here's your circle, but it's kind of like this. Like it's being stretched like that. So it's like it starts here and then it curves in towards the board like that. It's going to be a little hard to see. But let me show you. Yeah, it's hard to graph it. Your graph's gonna have multiple choice stuff in some graphs, okay? But because it's in general pretty hard to graph. Let me show you.
There's not even head.
Wait, where is it? Here it is, right here. See, if I look at it in terms of the YZ plane, it's a circle of radius 1. But if I look at it at the x, it's circular, but x is oscillating between -1 and 1. So it's that's what I was trying to graph right here, okay? Yeah, it goes in, it goes towards us, and then backwards like that. But it is rotating in this direction. Okay? Yeah. So what we're gonna do, is it's not time. So let me just show you guys what we're gonna continue. We're gonna do what you guys finished off in chapter 12.6. Here's a cylinder. Here's where I was telling you things are gonna overlap. Here's a cylinder. Here's a hyperboloid. Like this. Luckily, you won't have to graph them, okay? But that's what's happening. And what we're gonna do is we're gonna find the vector function that describes the intersection curve of those two surfaces. Okay? That's right, baby. Woo! We're gonna have to do that. We're gonna do that when we come back next week. Well, we have a what? A review. Probably not in class, but I might host one at the Math and Engineering Center. Okay. Okay.